AI Paper Podcasts on data engineering for scaling LLM terminal capabilities by researchers from NVIDIA, Pi et al., February 2026.
Key Insight 1. Training autonomous terminal agents like Claude Code is currently bottlenecked by the sheer cost and scarcity of multi-turn interaction data.
Key Insight 2. The researchers solved this with Terminal Task Gen. It's a pipeline combining adapted static data sets like math, code, and SWE with LLM-generated synthetic tasks built from primitive skills.
Key Insight 3. Using this data, they trained Nemotron terminal models based on Qwen 3. The results are staggering. Their 32 billion parameter model jumped from a 3.4% to 27.4% success rate on Terminal Bench 2.0. That actually outperforms the massive 480 billion Qwen 3 coder.
In Key Insight 4, the most surprising finding, filtering out failed or incomplete synthetic trajectories actually hurts model performance.
Right.
The models need to see mistakes to learn how to recover. So if you are an AI researcher, an ML engineer, or really anyone building agentic workflows, we are going to transition into a deep dive on how you can actually apply these data engineering strategies to your own pipelines.
Yeah, the headline numbers are flashy, but what this paper reveals about data curation, that's going to change how a lot of us train agents moving forward.
Okay, let's unpack this. We have great foundation models right now. They write brilliant code, they reason through complex logic puzzles.
Okay.
But the moment you drop them into a raw command line terminal and ask them to just operate seamlessly, use tools, navigate a file system, debug, they stumble hard. Why is this such a massive hurdle compared to building, say, a good coding assistant?
It's the data bottleneck. I mean, frontier models use undisclosed training mixtures, which forces researchers into this really costly trial and error loop.
Yeah.
And generating agentic data is fundamentally different from standard QA data. It's stateful.
Because it requires pre-configured environments.
Yes, exactly. Complex dependency files. And this is the big one. Capturing expensive multi-turn trajectory rollouts where the agent actually interacts with a live system.
Receiving standard output, processing it, deciding the next action.
Yeah. And the field usually tries to solve this by building more complex agent scaffolds.
Right, like intricate multi-agent systems or wrappers.
Yeah, heavy tool APIs. But this paper takes a totally different route. They just focused on improving the underlying model itself through brute force, high-quality SFT data.
Supervised fine-tuning. So they approached this with a two-pronged solution called Terminal Task Gen. The first prong is dataset adaptation.
Right, adapting what's already out there.
Exactly. They took existing high-quality prompt datasets, math from Open Math Reasoning, code from Open Code Reasoning, and software engineering from SWE Bench.
Which is basically the gold standard for real GitHub issues.
Yeah. And they adapted them into the terminal bench format. What's crazy is the mechanics of this. This doesn't even require an LLM in the loop.
Right, which is huge for compute budgets.
They just mapped instructions into a template and placed code files in a Docker environment. It's a highly efficient way to build general foundational reasoning at scale.
But obviously, static data has limits.
Right.
It doesn't teach the model the nuanced tool interactions.
Yeah.
Which leads us to the second prong, synthetic task generation.
This is the targeted approach. This is where they used DeepSeek v3.2 as a teacher model to create brand new tasks.
And they broke this down into two synthetic generation methods, seed-based and skill-based.
Right. Break down seed-based first.
So with seed-based, they take an abstract problem, like a math or science problem, and force the LLM to wrap it in realistic software engineering requirements.
Like reading inputs from a file path.
Exactly. Reading inputs, writing results out, and crucially, generating PyTest scripts to verify correctness.
So forcing abstract logic into real system constraints.
Yeah. But the skill-based generation is even more interesting. They used a taxonomy of 9 domains.
Like data science, security, system admin.
Yep. And within those, they combine 3 to 5 primitive skills to synthesize entirely novel tasks.
But this brings up a huge logistical issue. If you let an LLM write a raw Docker file for every synthetic task, it's going to hallucinate dependencies.
Oh, absolutely.
Yeah.
The build fails, you waste GPU cycles.
That's dependency hell.
It really is.
But they had a massive logistical win here. Instead of generating a unique Docker file for every single task, which is slow and error-prone, they used just 9 pre-built domain-specific Docker images.
Which turns the whole fragile pipeline into an industrial assembly line. It is brilliant.
It really is. And point out the technical infrastructure for the listener because it's a masterclass in MLO scale.
Yes, so to orchestrate this massive trajectory generation, they use the Harbor framework extended with Singularity,
Right.
which is common for HPC clusters since they don't usually allow root Docker access.
For security.
Right. And then they evaluated with Daytona Cloud sandboxes.
Okay, so we briefly need to explain how the models actually interact with this data. Enter the Terminus 2 agent framework.
Yeah, Terminus 2, it is so stripped down and elegant.
Unlike coding agents with specific tool APIs.
Right, there's no specialized search file API here. Terminus 2 just gives the model an interactive TMUX session in a sandbox Docker container.
So it's just raw terminal output.
Exactly. The model outputs a JSON containing its analysis, its plan, and its exact keystrokes.
Literally outputting text like credol plus C.
Yeah. And there's also a duration field in that JSON.
To wait for execution, so it naturally handles asynchronous tasks.
You get it.
Okay, here's where it gets really interesting. Let's dive into the ablation studies.
The trajectory filtering experiment.
Yes, because common ML intuition says you only train on successful data.
You want to show the model the golden path.
Right. But when they filtered the synthetic tasks to only include successful trajectories...
The performance completely tanked. It dropped to 5.06%.
Crazy.
But when they used no filtering, meaning they kept all the messy, failed, or incomplete trajectories.
Performance skyrocketed to 12.4%.
It more than doubled.
And let's discuss why this matters to the listener. Keeping the failures exposes the model to realistic error states.
Yeah, a terminal is chaotic.
Exactly. It teaches the model recovery patterns, how to read a traceback, realize it messed up, and try something else.
Right. And what's fascinating here is their context window findings. They tried long context SFT.
Like 65K tokens versus the standard 32K.
Yeah. And surprisingly, extending the context actually hurt performance.
You'd think more history equals better problem solving.
You would.
Yeah.
But the long tail trajectories were just too noisy. Like the model getting stuck running YOLO in an infinite loop.
Distracting from the core lessons.
Exactly. Tighter constraints enforced better data quality.
And we also have to mention the curriculum learning finding.
Oh, yeah.
A fancy two-stage curriculum, adapters first, then synthetic. It lost to a simple single-stage mixed training approach.
Sometimes we just over-engineer these pipelines. Mixing it all together was just better.
Okay, let's bring it all together with the mind-blowing scaling results. They used this data, which is now open-sourced as terminal corpus, to fine-tune Qwen 3 models, 8B, 14B, and 32B, creating the Nimotron terminal family.
Let's lay out the numbers for the ML engineers listening, because the gains are ridiculous.
Go for it.
The 8B model went from 2.5% to 13.0% accuracy.
A 5-fold increase.
Yeah, and the 32B model, it went from 3.4% to 27.4%.
And we have to emphasize the David versus Goliath aspect here. The 32B Nemotron terminal outscored the 480 billion parameter Qwen 3 coder.
Which only got 23.9%.
A model, a fraction of the size.
And their 14B model outscored the 120B GPT OSS.
It's wild, but we also need to highlight the domain breakthroughs.
Right, because this really proves the point. In categories like data querying and model training, the base models literally scored 0.0.
Could not do a single task.
Nothing. But the 32B fine-tuned model hit 60.0 in data querying and 50.0 model training.
Which proves that simply scaling parameter counts is completely insufficient for terminal capabilities.
You need this specific type of environment interaction data.
So what does this all mean? Summarizing the ultimate takeaway for your own work high-quality, diverse trajectory data, complete with errors and recovery, is the ultimate cheat code for agentic capabilities.
It punches way above pure parameter weight.
Exactly.
And if we connect this to the bigger picture, both the Nemotron terminal checkpoints and the terminal corpus dataset are available right now.
On Hugging Face.
On Hugging Face.
Yeah.
You can go experiment with them today.
Which leaves us with a final provocative thought. If exposing LLMs to failed command line trajectories makes them significantly better at problem solving,
Yeah.
could we purposely design intentional failure curriculums?
Oh, wow. Like chaos engineering for agent training.
Exactly. Imagine applying this to agents operating physical robotics or live server crisis management.
Right.
Training them not just on the happy path, but exclusively on how to survive and recover from absolute digital catastrophes.
Throwing them into the fire so they learn resilience.
It's fascinating to think about. That does it for this deep dive. Thanks for listening.